is 8:59. 16 or 15 students joined. What's up? Well, we had a discussion on the exhaustive search techniques, that's BFS, DFS, iterative deep depth first search, and bidirectional search. Those are uninformed searches, or you may call them as blind searches also. Now that we need to have a discussion on the heuristic search techniques, where when there are more number of solutions, you need to be finding out a solution that's more effective, or you may call it as an optimal solution. So you need to be reaching a goal state effectively. That's the basic objective. So when in that context, this is better than the previous approach because this will follow certain strategy. This would follow certain strategy. So it is going to improve the efficiency of the search. So when it is going to improve the efficiency of the search, it will not consider the factors such as systematic approach and completeness approach, but definitely finds a solution. It might not find out the best solution, but whatever solution it gives you is a good solution. If you use the heuristic search technique, which is going to determine the best among the several options that are available, it might not be the best, but definitely it is a good solution. For example, you may consider the traveling salesman problem. It's going to, if you consider the general approach, there will be several solutions. But which among them is the best solution can be obtained using the heuristic search techniques. And there are two types of heuristics over there. One is the general purpose heuristic, the other one is special purpose heuristic, just like general problem solving and the specific problem solving. When we say general purpose heuristics, these are useful in solving various problem domains. That means can be applied to several types of problems. When it is specific, it applies to a specific domain only. Okay. So these searches, they are definitely going to use the domain knowledge. Some kind of domain knowledge will be used. That's the reason we call them as informed search techniques. The previous one, we call them as uninformed. The exhaustive searches, we call them as uninformed search strategies, and these we call them as informed search strategies. In the last class, I gave an introduction to this. In the last class, I gave an introduction to this. I'm continuing with the session. See, one of the well-known method is the branch and bound search technique, which we also call it as the uniform cost search. And in this, we use a cost function normally denoted by g of x. And what does this g of x normally specify is, this is going to specify the least cost path. That means when you have a start state and you start moving from the start state towards the goal state, you need to be considering the path length from the start state to the. So far, whatever nodes are expanded up to that particular state, we need to be considering the least path among the all available paths. So since this is going to expand the least cost path, this is also sometimes called as uniform cost search. Uniform cost search. So this we normally call it as the heuristic function, the g of x or h of x, something like that. We call it as the heuristic function. Let's consider the simple example. See, here you have 4 cities: city 1, city 2, city A, city B, city C, city, and every city is connected to other city. So you need to be choosing a starting state. Let me say that city A is the starting state, and from this starting state, you should be able to visit all of the cities and reach the starting state again. That's what traveling salesperson problem is. See, earlier we have seen how it can be achieved using a general, but there's no standard procedure can be applied. You can choose anything. You can go from city A to city B, then city B to city D, and then city to C to C, city D to C, and then reach A. Or you can initially choose A to C, and C to D, D to B, and then B to A. Or you can go with A to C, C to B, B to D, and then A. So there are different types. But what is the optimal solution? What's the effective solution? That's important for us. That's important for us. So let's consider this algorithm in order to understand that, but in order to solve the particular example. As usual, we'll go with, as usual, we'll go with the start state and the goal states. Those are the initial inputs, and then we'll go consider certain variables. See, more or less all the algorithms are going to the same grounds. You may observe this similarity in presenting the algorithm: open, closed, node, successors, and found, and whether there is a solution or not, output. So what will be the initial state? The root node will be the initial state, or whatever node that you are going to consider will be the initial. Is empty, and initial state of found is false. So you need to repeat these steps. How long would you repeat these steps? As long as there are nodes in the open list and the state of found is false, you keep on going this. So once this condition is goal node, if this current node is not goal node, then you need to put this node into the closed list. That is, now the closed list is not empty, that you will have the first node. Into the closing list, and then you are going the successors of the closed list. And while finding out the cells, you will be the starting position. So initially the goal of this, what will be the G value over here? The G value would be 0. 1 second. A network issue, 1 second. Hope this paint screen is visible to you. Is this visible?
Yes, sir.
Thank you. So I'm considering A as the initial state and the G value is 0 because that's the starting state. And from city A, what are the possible cities that you can visit? You can visit city B, you can visit city C, or you can visit city D. Which city is to be visited depends on this heuristic value. Now, what is look at this diagram. From A to B, what is that length? You have 10. And 10 plus this particular value, 0. So let's consider that as the current path length from A to B. So 10. Next, from A to C, what's the length you have? 15. And A to D, what's the length you have? 20. So 0 plus 15, this is the current path length. That's how the G value would be calculated. This is 15 and this is 20. So from A, you can reach B, you can reach C, you can reach D. Now, which node should be next explored or expanded? See, according to the algorithm, it says initially you consider this. Is this the goal node? No. You have to visit all the cities and then finally reach that state. So out of these values, what is the least value, least heuristic value? The least heuristic value is 10. This is the least heuristic value. So you have to expand that node. You have to expand. So while expanding this node, what you do, you will be initially placing this node, this A into the closed list. A will be passed into the closed. That's according to the algorithm. See, you have the algorithm. Remove the top element from this, call it node. If node is the goal node, this is not the goal node. So what you do, you put that node into the closed list and then find the successors. You have found the successors. Now this closed list is going to contain A. That's how you have to understand. Now, if you expand this, see, A is already, that's the starting point. What other cities you have to visit from B? The other two cities that you have to visit from B is C and D. Now, what should you do is, you need to compute the heuristic value for C, the heuristic value for D. That means the path length from the starting position to the current node. So what will be the path length from the car? See, it's up to this position, we already know it's 10. Now, from B to C, what's the length? B to C, what's the length? It is 35. So what will be the total length for reaching the C? It is 10 plus 35, totally 45. So the heuristic value for this would be 45. That's how the expansion goes. Similarly, D, what will be the value? It is 10 plus 25, 35. So these are the values. Now, what is there present in the list? Initially, A was present in the open list. Initially, A was present in the open list. That was removed. And since that's not the goal node, that was sent to the closed list and that has been expanded. B, C, D. And all these three nodes were placed into this. All these three nodes are placed into this open list. Now what happened? What did you do? And these are organized in the sorted order. That is 10. That means we need to choose the least value, 10, 15, 20. And this node is now removed from the open list and that's expanded. Is B the goal node? No. Say, if you want to have the complete precision, that's how you have to write down. Now this B will be added to this closed list and B will be expanded. Its successor nodes are C and D. Now find out the heuristic values. 45. The heuristic value of C is 45. The heuristic value of D is 35. So these are already present in this. But now see, this C and D are already present in this. No, but the values of these are changed. The values of these are changed. So according to this, what is the least heuristic value? This C is with respect to 15. This D is with respect to 20. That is A to C is 15. A to D is 20, whereas from this A to B to C is 45 and A to B to D is 35. Now, if I insert these values also, what happens now? This is with respect to 15, this is with respect to 35, or you can, since they are already present in this, you can add them, but you have to update the weights. That's how it goes. So, suppose if you go with the wrong assumption that all these values are there, the repetition of what is the node that will be next expanded, because it has this is C to D means what the value will be? It's 35. So it will 15 less 30, 35. What will be the value over here? 15 less 35, it is 50. There are network issues still that way. And then C to D, what's the length? It is C to D is 30. So what will be the total value over here? 15 plus 30, it is 45. Okay, see now this is the one. See, with respect to see these initial values, this is removed. The initial value of this is 20, whereas the new value of this is 45. The new value of this is 35. The new value of this is 50. The new value of this is 45. Now find out the smallest value among all these. What's the smallest value? This one has the smallest value, so this will be expanded. This will be expanded. When this is expanded, what does it contain? Consider their successor nodes will be B and C. Now find out the heuristic value. What's the heuristic value? What's the heuristic value for this? You need to consider D to B and then D to C. D to B, it is 25. So it is 20 plus 25, 45. Next, heuristic value D to C. D to C it is 30. 30 plus 20, it is 50. Now, all these values, see, you do have repetition, but the values, heuristic values are differing. Heuristic values are different. Among all these values, which is the smallest value? This one is the smallest value. So, next node that will be expanded is this one. See, you have D over here. You also have D over here. But so, what is the node that's having the least value that will be expanded? So, how many children will be? I've drawn two lines over here, not necessary. What will the successor nodes for this? A to B, B to D, and then D to C. Are you getting this? So,
Yes, sir.
what will be the heuristic value? Over here, so D to C. D plus 30, 65. The thing that you understand or just say, I'm using paint. This might not be clear for you. I'm choosing starting state. I'm choosing a starting state, and if it is not the goal node, what am I doing? It this is being passed into the closest state, and then this is being expanded. When it is being expanded, all the nodes will be, all the successors will be taken into consideration, and their respective heuristic values will also be taken into consideration. They will be ordered in the open list, and whatever modified. And among all the available heuristic values, you need to choose the node that has the smallest heuristic value and then go for the further expansion. That's how the procedure goes. This is what the branch and bound strategy is. This is what the application of the algorithm is. See, a small discussion on this. The shortest path is always chosen for extension. This is what the path for reaching to the goal is certain to be optimal, but it is not. See, it might not find out the solution immediately. Getting the solution immediately, and this is here itself. About this. Yes, this network issues I am to come out and join again frequently. Okay. This is what regarding the branch and bond approach. There is another kind of strategy called generated as and check out whether the solution is a road or not. It's a climbing. And this hill climbing normally uses the generate and test strategy. This is going to use the generate and test strategy. And this hill climbing does not fall under this, the heuristic search, but also uses the heuristic. So it is called as a local search technique. But this hill climbing, it's not completely under the heuristic search techniques, this hill climbing method. It uses the local searching method. So it belongs to both the categories, heuristic search technique as well as the local search technique. So this is an optimization technique that belongs to the family of local searches. And this is normally used to solve problems which might have many solutions. So there could be several solutions possible, and if you want to choose the one that normally is better than the others, then this procedure is applied. And again, we can discuss the same thing using the traveling salesman problem, the hill climbing also. The traveling salesman problem. In the previous slide, we had a discussion on this using our branch and bound approach. That too, least cost branch and bound approach. We can also solve that using the hill climbing approach. And when you consider the hill climbing approach, it normally follows the depth first order. Depth first order. And how are we making? How are we going to make the choices, the options? How do you go to the next node? We use the heuristic value. So this is important. So that's the reason, even though it falls under local search, why are we calling it as local search? Means it does not use any other knowledge over here. It is going to use this knowledge only, a limited knowledge. That means the search takes place only confining to the domain. That's the reason we call it as local search, but definitely uses the heuristic value. So it falls under the heuristic search technique. Okay. And this is the algorithm for it. And how does the algorithm go? Just as the previous case. See, more or less, if you find out all the algorithms that have been presenting in these slides are more or less similar, if you clearly make a note of this. See, the initial input is start and goal states, the local variables, and then the output. So the start node, whatever is the start node, that will be placed in the open list, which is being maintained as a stack, and the status of found is false. See, and while open not equals to empty and found is equal to false, repeat this process. Definitely found is false and open is not equal to empty. So what are we going to do? Remove the top element from this open list and call that as the current node. If that is the goal node, if the current node is the goal node, definitely you will come out of this loop and present your solution. Simply say that you have obtained the goal state. Suppose if that's not the goal node, then you expand the given node. That means find the successors of the given node. And after finding out the successors, you need to sort them by the heuristic value. We need to sort them by the heuristic value. And when you consider this heuristic value from the start state to goal state, we need to consider, and then you need to add them to the open list and repeat the process. See, almost all the algorithms more or less appear to be similar, but there is a slight change. Kindly make a note of that change. Okay, and you see in most of the algorithms, I've been using the same set of variables and same set of algorithmic statements. Okay, so in the previous one also we have used, but we have used a different list, closed list. Is this having a closed list? When compared to the branch and bound, we are not having the closed list. You should make a note of that. This is simple. There are different types of hill climbing, but we are going to consider the simple hill climbing algorithms. And with respect to this hill climbing algorithm, let's consider a simple problem, blocks word problem. And what does this blocks word problem tell you is, these are independent blocks. which are placed as a stack, placed one on the other. So we have four different stacks, A, B, C, D. Four different stacks are there, and these four different stacks are organized in the initial state this way. So the lowest one is B, above that is C, above that is D, above that. And from this initial state, you need to move to the goal state. This is what our goal state is. And when you move from this initial state to the goal state, there are certain constraints. You need to assume that these are available on a table. This initial state is available on a table. At a time, you can move only one block. That means you can remove this block and place on the table, or you can place it on some other block. Okay, and then we need to consider the heuristic value also during the expansion. So at the constant here over here is at a time you can remove only one block. See, this is the initial state. I can remove only A from here. I cannot directly remove D and place over here. Only the top element should be removed. This one should be removed. Okay, and when you consider the next possible expansion or next state, we need to be considered see, I'm disconnecting frequently due to network issues. There is an interruption in the class, delivery of the class.
So the main function ఏ parameters తెలుసుకోండి.
Am I audible? Hello.
Yes, sir.
Sorry, I'm a frequent network issues. I have to find out a solution. So hope this slide is visible to you now. Yeah. See, the highest value of B would be 0 because it is there on the table, and the other nodes, this is one level above it. So the heuristic value would be -1, this for -2, and the heuristic value of this is -3. So the total heuristic value for this structure is -6. So this is the initial state. This is the initial state. Now, what does the solution of Blockworks problem tell you? At a time, you can only move the block that's available on the top of the structure, and that can be placed on another block or that can be placed on the table. So A is removed, and A is placed on the table. So when it is placed on the table, what will be the heuristic value of that particular block? That would be immediately 0. That would be immediately 0. So the heuristic value of A is 0 now, the heuristic value of B is 0, the heuristic value of C is -1, and the heuristic value of D is -2. So what's the total heuristic value over here? It is 0 plus 0, -1, -2. This is totally -3. Is there an improvement in the heuristic value? Earlier it was -6 and now it is -3. So always you need to see an improvement in the heuristic value. So it is decreasing, it is increasing from -6 to -3. Now, then in the next step, what should you do? You have to remove D from this structure. Now, should it be placed on the table or can it be placed on this? See, what's our goal structure? The goal structure says that on A, you should not have B. Sorry, you should not have D. So you cannot place D on A. So that should be placed on the table. So in this sequence, A, D is placed on the table. When it is placed on the table, what's the heuristic value for that? It is 0. So the heuristic value of B is 0, the heuristic value of A is 0, the heuristic value of D is 0, and C is one level above the B. So the heuristic value of C is -1. So what is the total heuristic value? All these are zeros and this is -1. So this is -1. Is there an improvement in the heuristic value? Yes, there is an improvement in the heuristic value. So it started with -6 and then with -3, an improvement, and then -1. Now I remove C. Now can I place C on A or D, or should it be placed in the table? If I place C on A, will it be in a possible goal state? No. When I place this on this, will it be a possible goal state? No. In the structure that's available in the goal. So it's better we place the C on the table. The simplest way of doing, because this is simple hill climbing, we place it on the table. Now when you place it on the table, all the 4 blocks are on the table. They are horizontally placed in the available on the table. So what will be the heuristic values of 4, 0? So value of this is 0. See, with minus 6, we found on finding the improvement in this. So it is growing up. It's growing up. Now this. Now all the blocks are on the table. Now what's our goal? What does the goal say? The lowest one should be A. Above that you should have B. At a time only one black could move. Now what happens? This B is placed over A. So this is what the step you are going to have. When B is placed on A, is this the right one? Yes, this is in the right position. This is in the right position as per the goal. So this is 0 and now this will be plus 1, not minus 1. See, this is not in the right position. That's the reason we have kept it as minus 1. Because our assumption is that if they are in the right positions, plus 1, not in the right correct positions, minus 1. So since this is in the right position, now the heuristic value would be positive. So now the positive value is plus 1. Next step, what should we do? According to the goal, on B we need to place C. So now C will be placed on D. Now once C is placed on this, what will be the heuristic value? A, this is 0, this D is 0, this is plus 1 and this is plus 2. So totally 3. So heuristic value is 3. And the next step, place D over this. Now the heuristic value, this is 0, this is plus 1, this is plus 2, this is plus 3 because they are in the right position. That's the reason you are going in the positive sense. And these are not in the right direction, correct position. That's the reason they are considered minus values. So we started with this initial structure and reached the goal structure. And at every step, you need to observe there is an improvement in the heuristic value. See, H1 is equal to minus 10, and then the second point, the heuristic value is minus 3, next minus 1, then 0, then plus 1, then plus 3, and then plus 6. This is how the problem is to be solved. And are we using any other knowledge over here? We are just performing with available blocks only. That means no extra knowledge is being used. That's the reason this is called as local set. Even though it is using heuristic value, this is called as the local set. This you need to understand. That's important over here. Okay. This is how the the blocks world problem is also be solved using the hill climbing approach. The 8 puzzle problem that we have considered earlier, that can be also solved using the hill climbing approach. See, it is up to us. Here we need to have a start set and then a goal set and then apply the procedure. As simple as that. Now there are certain problems with this hill climbing approach. Now if you clearly observe what is happening in this, there is an improvement in the heuristic value, that which is gradually increasing. That's the reason this is called as hill climbing. Like, going this become the see, is
company రాస్తాను అన్నమాట. సో సి ఈక్వల్ టు ఏ ప్లస్ సో ఏ ప్లస్ రాస్తానా రాయదు. ఏ వాల్యూ నాకు తెలుసా తెలియదు. ఆ ఏ వాల్యూ అంటే ఆ బ్లాక్ లో ఉంది. సో ఎక్స్ వాల్యూ వై వాల్యూ
very sorry for the current state of affairs, Amma.
ఓకే ఏం చేస్తున్నాను ఇప్పుడు రిటర్న్
You have
చేస్తున్నాను.
to
వాడంటే రిటర్న్ నథింగ్ బట్ ఎనీథింగ్ అంటే ఇప్పుడు ఈ యాడర్ ఫంక్షన్ రిటర్న్ చేయలేమన్నమాట. సో
dissatisfied with the current network situation.
Some is okay. Percentage is and that's C and that's so percentage is D కాదు percentage F నేను చెప్పాలి. అయితే ఏముంది థ్యాంక్ యూ వెరీ మచ్. ఓకే సో ఇండెక్స్ ఫ్లోర్ ఓకే ఇది యాడ్ చేసేసాను. ఇందులో యాడ్ చేసేసాను. ఓకే ఇప్పుడు ఒకసారి రిజల్ట్ చూద్దాం. సేవ్ చేస్తున్నాను. ఓకే కంపేర్ చేస్తున్నాను. చెప్పండి 7 అంటే ఓకే ఎంత కావాలి సో లాస్ట్ లో ఆ ఇండిషన్ తెలుగు 60% చెప్పండి 41 అనేది లాస్ట్ లో
Hello.
because this is example is the y function different okay y function so parameters ఏంటి parameters ఏమి తీసుకోవాలి parameters ఏమి ఇది screenshot పంపించవచ్చు ఓకే సో y function కనిపించలేదు కానీ అప్డేట్ రెండు నెంబర్ యాడ్ చేయాలి కానీ నెంబర్ పంపించలేదు parameters లేదు అక్కడ కూడా ఓకే
Hello.
Okay.
Is one problem. Flat is another problem. And there is one more problem called as ridge. In ridge, what happens? All these are the problems with respect to hill climb. So here is this is an area of such space that is higher than the surrounding state, and then as the ridge problem. It is an area of such space that is higher than the surrounding areas, but that cannot be traversed by single moves in any one direction. So this is a special kind of local maximum problem. So here we need to apply two or more the heuristic values, and then accordingly choose which one is more feasible. So these are the three problems with respect to the hill climbing. Meghna,
Sir,
Meghna,
yes, sir.
just post the attendance. I'll continue the session in the next class. Too many interruptions. Sorry.
Okay. ఇప్పుడు the returns value right? So this is no returns value.
There will be no network issues. There are no network issues only. I'll go ahead with the class, or else I'll not go ahead because it's my problem. It's a problem from my side. Too many interruptions. Okay, he may leave the class session and join the other class.
Okay. So ఇది ఎప్పుడు ఇస్తున్నా ఓకే ఏం చేస్తున్నాను అన్నిటిని యాడ్ చేయాల్సి ఏం చేయాలి ఓకే మనకు ఈ వాల్యూ తెలుసా తెలుసు ఎఫ్ తెలుసు తెలుసు ఈ వాల్యూ ఎలా ఉంది ఏ వాల్యూ ఎంత టీ వాల్యూ ఎంత ఎఫ్ఐ ఎంత అవుతుంది టీ వాల్యూ ఎంత తెలిస్తే ఎఫ్ఐ ఏం చేస్తున్నాము రిటర్న్ ఈ ప్లస్ చేస్తున్నాము